Section 8.1 is basic integration formulas. Now, a lot of this you learned in Cal 1, or at least you should have learned it, but you've slept since then, so you might have forgotten it. So we're going to bring some things back to the forefront of our memory. This table consists of a lot of integration formulas that you should already have memorized. Definitely the first 7 of these. The ones you don't have to worry about memorizing for this course is the hyperbolic trig functions. And then these that are the inverse trig functions. When we get to, I believe it's section 8.4, we're going to learn a technique of integration called trigonometric substitution that will negate memorizing these. But if we encounter problems where we need these formulas before we get to section 8.4, I'll go ahead and use these formulas then. Most all of these need to be memorized. This one comes up an awful lot. And so you need to make sure that you have this one committed to memory. The integral of secant is equal to the natural log of the absolute value of secant x plus tangent x plus c. Now in our first example problem, we're going to be asked to complete the square in order to evaluate this integral. So I feel compelled to review completing the square just to make sure that you still remember how to do that. Whenever you're asked to complete the square, or if you think you may need to complete the square in order to solve an integral, first thing you want to do is make sure that the leading coefficient is 1. So if you have a quadratic expression ax squared plus bx plus c, in order to make the leading coefficient 1, what you're going to do is you're going to factor an a out of that, and that would leave you x squared plus b over a x plus c over a. And you know that this is correct because if we were to distribute that a back through, then we would end up with ax squared plus bx plus c. When we're completing the square, we're really interested in having the x's grouped together. So probably when you rewrote this, what you would want to do is, let's just leave it like this, pull the c out and leave the x squared and the x terms together in parentheses, and then just pull that c out. That will help us when we get to our second step, which is to add a constant half of b squared inside the parenthesis right here, and then subtract that same value for a net change of 0. By adding that particular constant inside this parenthesis, it will allow you to factor your quadratic in this form, x plus half of b quantity squared. So these are the steps for completing the square. So in example 1, we're told to complete the square in order to evaluate this integral. So we're going to start by doing some scratch work. We have the expression 8x minus x squared, and I said that you want to start with a leading coefficient of 1. Right now our leading coefficient is -1. So what I'm going to do is I'm going to pull that negative out, and that's going to leave me with x squared minus 8x. Then we said that we need to add half of this quantity squared. Well, half of -8 is -4, and when we square that we get 16. But what I added here was not just a 16. This negative gets distributed back through, so that would be a -16, and to counteract adding a -16 here, I'm going to add a +16 so that this side of the equation is mathematically equivalent to this side. And if I were to distribute that negative and combine like terms, I would end up with what's on the left-hand side. So just to make life a little easier, I'm going to write my positive term first, minus, and now because I've added that 16 to this quadratic expression, this should factor into x minus 4 quantity squared. Notice when I added this +16 and that -16, my net change was 0. So the question was, by adding the 16, did I force it to be a perfect square? And the answer is yes. If you add this particular constant, which is half of whatever the x is multiplied by squared, you force the quadratic to be able to factor into this. We're forcing a fit there. What I said was half of b is whatever the x is multiplied by. Remember, we have ax squared plus bx plus c. Those are the a, b, and c that I'm referring to. So half of b would be -4, square and -4, and you get a 16. But because that 16 was multiplied by a -1, to counteract that net gain of -16 to this first expression, I have to add a +16 so that the net change to this expression is 0. So now I can write this as the difference of two squares. So that means that this integral can be rewritten as the integral of dx over the square root of 16 minus x minus 4 quantity squared. Now it helps if you remember that the integral of dx over the square root of a squared minus x squared is equal to sine inverse x over a. That was in that table from above. So that means that I can do a substitution here, and we're going to let u be equal to what? So what is du equal to? Just dx. What is a going to be equal to in this formula right here? A is going to be equal to 4. All of this to the left is my scratch work. Over here then, that's going to give us the integral of du over the square root of 4 squared minus u squared is going to be equal to sine inverse u over 4 plus c. Do I want to leave that as my final answer? Never. If the original problem has x as its differential, my final answer has to have an x in it. So this is going to be equal to sine inverse x minus 4 over 4 plus c. And that would be our final answer. The question was, how did I get a equals 4? In the formula for the integral, we had a squared minus x squared, where a is a constant. Well, 16 I can write as 4 squared. So that's why I said a was equal to 4. I just rewrote 16 as 4 squared. Moving on then, example 2. We're asked to evaluate the integral of cosine x sine 2x plus sine x cosine 2x dx. You're allowed to use your trig formula sheet on the exam, so you don't have to memorize these trig identities, but I am going to remind you of the trig identities for the sum and difference formulas. Which sum and difference formula do you think I'm going to use here? Which formula seems the most appropriate? So I've got cosine sine plus sine cosine. Come over here and I see cosine sine, or sine cosine, and cosine sine. The others, they're the same. So this is going to be a sine formula, and because I have a plus between, I'm going to use the sum. So I could rewrite this integral using the sum formula for sines as the integral of sine x plus 2x dx. And that's going to be the integral of sine 3x dx. And the integral of sine is what? Negative cosine. So I've got a negative cosine, leave the angle alone, and because that x is multiplied by a constant, what's my constant going to be that I multiply by? It's going to be the reciprocal. I don't need a dx there, so it's going to be negative 1/3 cosine 3x plus c. If you did not see, or you did not remember about how we got that constant, what you could have done at this point is done a u substitution. Let's let u be equal to 3x. What is du equal to? 3 dx. So that means that 1/3 du would be equal to dx. So then coming over here, I could rewrite my problem as the integral of sine u times 1/3 du. And when I integrate sine, I get negative cosine. That constant just stays multiplied out front, and that's going to give us negative 1/3 cosine. And what was u equal to? 3x plus c. So this would be the final answer. Notice they're the same. Rather than do the u substitution, I think it will save you time and energy if you will remember when you're integrating a trig function, if x is multiplied by a constant, go ahead and integrate like you normally would. Integrate sine to get negative cosine. Leave the angle alone because calculus will never change a trig angle, and then multiply by the reciprocal of that constant that x is multiplied by. We have to use trig rules in order to change trig angles, and that's what the sum and difference formulas do, as well as other trig identities. Only trig can change angles. Calculus never will. In section 8.1, you're going to be seeing a variety of problems that will require a variety of different techniques in order to integrate. You have all of the necessary tools in order to be able to do these. It's just being able to remember them at the right time. That might be a challenge. And unfortunately, the only way to get good at doing this is to practice. In example 3, what we're going to do is use algebra to manipulate the trig identity into something that we can work with. Okay, because I don't know how to integrate dx over 1 minus sine x. Typically, when you see something like 1 minus sine x or 1 plus sine x, what I want you to do is think about multiplying by the conjugate, because that'll lead to something that we can then use a Pythagorean identity for. So let's do some scratch work here. So I start with 1 over 1 minus sine x, and the conjugate pair of that would be 1 plus sine x. And if I multiply the denominator by 1 plus sine x, I also have to multiply the numerator by 1 plus sine x so that the net value of this fraction right here is 1. Multiplying by 1 doesn't change the value of anything, it's just going to change the appearance. So when I do that, that's going to give us 1 plus sine x over 1 minus sine squared x. And if you remember your Pythagorean identities, we have sine squared plus cosine squared is equal to 1. And if I subtract a sine squared from both sides of this equation, I see that 1 minus sine squared x can be replaced with cosine squared x. So that's what I'm going to do. I'm going to replace this with the denominator with cosine squared x, and that's going to give me 1 plus sine x over cosine squared x. Then I can distribute that denominator, and that's going to give me 1 over cosine squared x is equal to, I'm going to write this as sine x over cosine x times 1 over cosine x. And 1 over cosine squared is secant squared, and sine over cosine is tangent, and 1 over cosine is sine, so this becomes secant x tangent x. So that means that this expression can replace this expression, and my integral can then be rewritten as the integral from 0 to pi over 4 of secant squared x plus secant x tangent x dx. I got us a little more room here now so we can actually finish this problem. So when I integrate secant squared, what am I going to get? So the integral of secant squared is tangent, derivative of tangent is secant squared. Do y'all remember that now? And then what's the integral of secant tangent? Secant. And our bounds go from 0 to pi over 4. So when I plug in my upper bound, that's going to give me tangent of pi over 4 plus secant of pi over 4 minus, and then plug in our lower bound, we get tangent of 0 plus secant of 0. And what is tangent of pi over 4? 1. Secant of pi over 4 is square root of 2. Tangent of 0 is 0, and secant of 0 is 1. When we distribute the negative here, that's going to give us 1 plus the square root of 2 minus 1, and this just ends up being the square root of 2, because the 1 and the negative 1 are going to cancel out when I distribute that negative across. On example 4, notice that we have an improper fraction in our integrand. If you have an improper fraction, you can use long division in order to simplify that fraction, and that'll change things. So we're going to use long division to rewrite the integrand here. So that means I'm going to take 3x plus 2 and divide it into 3x squared minus 7x. Remember, when we use long division, we're just looking at the first term. So 3x squared divided by 3x leaves us what? 3x squared divided by 3x is going to be equal to x. That's what goes on top here. Then we have to distribute that x across. So x times 3x is 3x squared, and x times 2 is positive 2x. The next thing you want to do is subtract. In order to subtract, we're going to change our signs, and typically what I'll do is circle them once they're changed, and then add. So 3x squared minus 3x squared goes to 0. Negative 7x minus 2x leaves us a negative 9x. And then I look at negative 9x divided by 3x, and that's going to give us negative 3. So x minus 3 is going to be our integrand here. Let's see what our remainder is. So then we're going to distribute the negative 3 times x gives us a minus 9x minus 6. Change your signs and add, and that's going to give us a remainder of 6. That means that I can rewrite this integral as the integral of x minus 3 plus 6 over 3x plus 2. Then we can integrate this a term at a time. So that's going to give us the integral of, I'm going to write this as x minus 3 dx plus the integral of 6 over 3x plus 2 dx. Integrating x is easy. That gives us 1/2 x squared minus 3x plus, and then to integrate this, I'm probably going to want to use a u substitution. So what would I let u be equal to? 3x plus 2. If u is 3x plus 2, then what is du going to be? 3 dx. So when I rewrite this, I do have a 3 here because that 6 I could write as 2 times 3. When I rewrite my integral, what constant am I going to pull out? A 6? Well, I need 3 of that 6 to go to the dx. So I'm going to pull out a 2, and then what I'm left with is du over u. And what is the integral of du over u? So the integral of du over u is the natural log of u. Do I want to leave that as my final answer? No, I do not, My final answer has to be in terms of x. So that's going to give us 1/2 x squared minus 3x plus 2 times the natural log of 3x plus 2 plus c. Do not forget the plus c. If you do, I'll take off a point. Number 5. Any ideas on what we're going to do with this one? There's your hint. If there's only one term in the denominator of a fraction, you can distribute that denominator. What allows you to do that is the rules for adding fractions. So if I have a over c plus b over c, because I have a common denominator, that means that I can combine the numerators over that common denominator. What we're doing here, what we're going to do here, is go in the reverse order. We have a sum over a common denominator. I'm going to break that sum up into two different fractions. This will be the integral of 3x over the square root of 1 minus x squared dx plus the integral of 2 over the square root of 1 minus x squared dx. Does everybody see what I did there? To integrate this first fraction, what am I going to do? I'm going to do a u substitution. What do I want to let u be equal to? 1 minus x squared. What is du going to be equal to? Minus 2x dx. Do I have a minus 2x dx in the problem? No. I have an x dx in the problem, but I don't have the negative 2, so I'm going to divide that negative 2 off of both sides of this, and that gives me minus 1/2 du is equal to x dx. I'm just taking these one at a time. So what do I do with that 3 that's in the problem? Pull it out. So that's going to give us a minus 3/2 with that negative 1/2 that I have, times the integral of du over u to the 1/2. By the way, I'm working these as if they're two separate integrals, just working them one at a time. And then at the end, I'll put my answers together. So this I could rewrite as negative 3/2 times the integral of u to the negative 1/2 du. And when I do that, what do I get? Add 1 to the exponent. 1 minus 1/2 is 1/2. Divide by the new exponent. Dividing by a half is the same thing as multiplying by 2, and that's going to give us negative 3 square roots of u, but u was equal to 1 minus x squared plus c. Now looking at the second integral. It helps if you remember that the integral of dx over the square root of 1 minus x squared is sine inverse x. So really all I have to do with the second integral is pull out that constant of 2, and that's going to give us 2 times the integral of dx over the square root of 1 minus x squared, and that's going to be equal to 2 times sine inverse x plus c. So putting both of these answers together, that's going to give us that the integral of 3x plus 2 over the square root of 1 minus x squared dx is going to be equal to negative 3 square roots of 1 minus x squared. That came from this first integral, plus 2 sine inverse x plus c. And that answer came from this second integral right here. And that would be our final answer. The question was, did I have to do a u substitution on the second part of this integral? And the answer is no, because if you look at the rule for the integral where you get sine inverse x, I have every piece of that in this problem. All I had to do was pull the 2 out of the integral. Then this piece right here looks exactly like this piece right here. So there was no need to do any u substitutions. All I did was distributed the denominator on the integral, broke this into two problems, solved each of these problems, and then at the end brought the answer together, the two answers together, and put it in one single answer. Example 6. This one is going to be a u substitution, but it is not a straightforward u substitution where I'm just going to do u and du and be done. Looking at this problem, what do you think u should be equal to? 1 plus the square root of x. All right, that 1 plus the square root of x I could rewrite as 1 plus x to the 1/2. I'm writing it like that so that it makes it easier to see what du is going to be equal to. Du is going to be equal to 1/2 x to the negative 1/2 dx. If I multiply both sides by 2 and get rid of the negative, that's going to give me 2 du is equal to dx over the square root of x. But what is the square root of x equal to? Well, if I look over here and I solve this equation for the square root of x, I get that the square root of x is u minus 1, isn't it? Right? If I just subtract 1 from both sides, I get the square root of x by itself right here, and then u minus 1 is the square root of x. So in place of that square root of x, I'm going to plug in u minus 1. I don't have a u minus 1 in the problem. I do have a dx, and I want to know what can I plug in for the dx. Well, if I multiply both sides of this equation by u minus 1, I get dx is going to be equal to 2 times u minus 1 du. Now this is what I'm going to plug in place of the dx right here. And in place of the u, I'm going to plug in, in place of the 1 plus the square root of x, I'm going to plug in a u. So now I'm going to rewrite my problem. And this is going to be the integral of 2 times u minus 1 du over u to the third. And what do we do when there's only one term in the denominator? We're going to distribute that denominator. But in order to do that, I might want to distribute that 2 first. So let's look at this. This is going to be the integral of, I'll go ahead and do all the distributing at once. That's going to give us 2u divided by u cubed minus 2 over u cubed du, distributing both the 2 and the denominator. Well, this u will cancel with one of the u's in the denominator, leaving me the integral of, I can pull that 2 out if I want, actually. That probably would have been a better thing to do. We're going to factor that 2 out. That's going to give us u to the negative 2 minus u to the negative 3 du. Yeah, it would have been better if I would not have distributed the 2, but rather pull it out. But those are one of those things that you don't see it until after you've done it. Hindsight's 20/20. So now we can integrate this, right? What is the integral of u to the negative 2? Add 1 to the exponent, that gives us a u to the negative 1. And then divide by a negative 1 gives us a negative 1. And then minus, and then add 1 to the exponent here, that gives us a u to the negative 2. Dividing by a negative 2 gives us a plus 1/2 plus c. Cleaning this up then, we get 2 times minus 1 over u plus 1/2 times 1 over u squared plus c. So our final answer here, when I distribute the 2 and replace u's with x's, that's going to give us negative 2 over 1 plus the square root of x, because that's what u was equal to. 2 times 1/2 is 1, so that's going to be plus 1 over 1 plus the square root of x squared plus c. So our final answer is negative 2 over 1 plus the square root of x plus 1 over 1 plus the square root of x quantity squared plus c. Sometimes when you do a u substitution, you have to solve for x in terms of u and then do a substitution within your substitution in order to get the problem where you can work it. Were there any questions about this one? This one got a little complicated. Number 7. Here we have the integral from negative pi over 2 to positive pi over 2 x to the cube cosine x. What I notice here is that these bounds are opposite of each other, and x cubed and cosine x are both odd functions. If we were to graph x cubed cosine x on the interval from negative pi over 2 to pi over 2, and I will step this at pi over 4, and we'll go from negative 1 to 1 and look at the graph. What do we notice about this graph? Remember, odd functions are symmetric about the origin. The area that's below the x-axis is exactly equal to the area that's above the x-axis, isn't it? That means that this will actually be equal to 0, because the area that's above the x-axis right here is equal to the area that's below the x-axis, and we're integrating from negative pi over 2 to pi over 2. So this wraps up section 8.1.